All right, welcome to Chapter 2, Section 7. We're going to be doing optimization. So in theory and application, we often want to maximize or minimize some quantity. An engineer may want to maximize the speed of a new computer or minimize the heat produced by an appliance. A manufacturer may want to maximize profit and market share or minimize waste. A student may want to maximize a grade in calculus or minimize the hours of study needed to earn a particular degree. So local maxima and minima. Before we examine how calculus can help us find maximums and minimums, we need to define the concepts we will develop and use. So let's look at the definition. Let me make this a little bigger. Okay, so F has a local minimum at A when you want to read definitions, the best thing to do is really kind of draw it out. So let's draw a graph. And so if we have a local maximum at A, if f of A is greater than f of x for all x near A. So what that really means is, let's say we have an A here. F of A is greater than all the f of x's around it. So it would look something like this, because it says near A. We can see that that gives us a local maximum. So the reason we call it a local maximum is because we're just talking about a certain region. We're talking about things near A. If we had a graph and instead of, notice the difference between the first definition and the second definition, now f of A is smaller than every other point around that value. And they're talking about just an area like this. F has a local extreme at A if f of A is a local maximum or minimum. The plural of these are maxima and minima. We often say max or min. It saves a lot of syllables. So some books say relative instead of local. The process of finding maximum or minimum is called optimization. And that's what we're going to be working on today. A point is a local max or min if it is higher or lower than all the nearby points. These points come from the shape of the graph. Now we have some other definition, and it's called a global maximum. What a global maximum is that at A, if f of A is greater than every other f of x for all the values in the function. So notice, let's just talk about it instead of reading. To know if you have a local, or sometimes called relative, maximum or minimum, it just means that in some region, like for example here, that's a local minimum. This is a local minimum. This is a local minimum. But also, not only is it local, it's global because it is the lowest point or the smallest point on the graph. So it is the minimum value. If we look at maximums, this is a local maximum. This is a local maximum. If you have a local maximum, it means that you know what comes before it and what comes after it. So endpoints don't count. We're only talking about things that we can see start somewhere close by and end somewhere close by. These are local max and mins. The global maximum or global minimum is the highest and lowest point on the graph. For example, this is the highest point and this is the lowest point. That's why they're global max and mins. So example 1, the table shows the annual calculus enrollments at a large university. Which years had local maximum or minimum calculus enrollments? Okay, so I'm just going to go straight underneath. Let's say this is 1257, 1324, still going up, 1378, up, coming back down, 1336, 1389 goes back up, and it's actually the highest point so far. 1450 is higher, 1523 is higher, 1582 is higher, 1567 will be coming down, 1545 still coming down, and 1571, we're about there. And none of this is to scale. It's just giving me a kind of a shape. And I can even connect the dots here. Let's say I connect the dots. I can see that here, at this point, I have a local minimum. And I can see right here, I have a local maximum. Also here, I have a local minimum. Okay? These are all local because they're the highest and lowest points in this area. Now, if we want to find, so that actually takes care of what years had local maximum or minimum calculus enrollments. The answer to that question would be 2003, 2007, 2009. So those are the 3 years where we have local maximums. The only one we have local maximum is 2007. Local minimum. Local minimum we have in 2003 and 2009. Now, that pretty much takes care of that. What were the global maximum and minimum enrollments in calculus? So global minimum is the smallest value. And we can see that that's going to occur right here at the end of the graph. So what year is that? That is year 2000. That's the that's the global minimum. And then we look through our numbers, and so far it looks like 1582 is our biggest value. That means this is also a global max. This is our global min. It means in the whole graph, they're the largest and smallest values. So the global maximum occurs in 2007. So points can be both local and global maximum or minimums. Okay, so finding maxima and minimum of a function. What must the tangent line look like at a local max or min? Well, we can see that this would be a local min at A, and it's horizontal. Maximum, local maximum at C, local maximum at F, local minimum at H. All of them have horizontal tangent lines. And that means that the first derivative has to be 0. There's one cusp. This right here is a cusp. If I want to find the tangent line there, it's actually vertical. And when things are vertical, remember the first derivative, which is the slope of that line, is undefined. So a critical number for a function f is a value x equals a in the domain where there's two possible conditions. Either the derivative at that point equals 0 or it is undefined. Like for example here, the cusp is undefined, but it's still a critical point. A critical point for a function f is a point, and they're calling this, so x would be a, and then whatever f of a is would be the y, where a is a critical number of f. Useful fact, a local max or min of f can only occur at a critical point. So it's not saying that critical points always have local max and mins. What it's saying is that local max and mins only occur at the critical points. So those are two very different things to say. So if we want to find the critical point of this function, we take the first derivative. So f prime of x is equal to 3x squared minus 6 times 2, which is 12 times x, plus 9. And we set that equal to 0. We don't have anything really undefined. This is just a polynomial. Polynomials are defined everywhere. So we have this function equal to 0. And first thing I'd like to do is I'd like to factor out the greatest common factor, which is 3. Because that'll make it a whole lot easier for me if I find that I can factor this. And I can factor this. This is going to be x minus 3 times x minus 1. That equals 0. So we have two conditions. Either x minus 3 equals 0 or x minus 1 equals 0. I add 3 to both sides, I get x equals 3, or if I add 1 to both sides, x equals 1. These are my two critical points. So we found the critical points, and f prime exists everywhere. It's still a polynomial. First and second derivative tests. Is that critical point a maximum or minimum, or neither? Once we found the critical points of f, we still have the problem of determining whether these points are maximum, minima, or neither. So as we can tell here, this is a maximum. This is a minimum. This is really nothing. There's nothing there. It has a corner, which means it's undefined, but it's not a max or min. If I follow this graph, I'm going from here up to that point, and then it's going up again. So it's not a maximum, and it's not a minimum. It's neither. The same thing is true here. This is also neither. Because it's going up and then it's going up. Notice on the maximums, before you get to the max, it's increasing, going to 0, and then decreasing. So if something's increasing and then decreasing, it's obviously going to be a maximum. If something's decreasing and then increasing, it's obviously going to be a minimum. So the critical numbers only give the possible locations of extremes. And some critical numbers are not the locations of extremes. Just what I said, not every critical value has a max or min, but every max or min occurs at a critical value. Only the critical numbers are the candidates for the locations of max and mins, which is what I just said. So f prime and extreme values of f. We have 4 possible shapes of graphs are shown here. In each graph, the point marked by an arrow is a critical number. So this is a critical point. This is a critical point. This is a critical point. And this is a critical point. What that means is the first derivative is 0. But we want to also figure out is what's happening before and after that critical point. Notice here, my slope is positive, which is what this says. And here, my slope is negative, which is what this says. And so if you go from positive to negative, you're going to have a maximum value. If you go from negative to positive, you're going to have a minimum. Notice here, the graph is always increasing here. This is always positive. We get to our critical point, and then we're still increasing after. That means it's neither. Here we're decreasing, and then we're decreasing. Again, for the same reason, it's not a max or min. When you have a max or min, you have to increase, then decrease. Min, decrease, then increase. If that doesn't happen, you don't have an extreme value. Here we go. The first derivative test for extremes. For step 1, find the critical values. To find the critical values, I say f prime of x. I need to find the first derivative. So we have 3x squared minus 12x plus 9. Looks like the same thing we had before. So we're going to set this equal to 0. 0 is equal. We're going to factor out that 3. And say this equals 3 times x minus 3 times x minus 1. And that equals 0, which gives me my critical points at x equals 3 and x equals 1. Okay? Now we want to figure out if they're local max or mins. And the way they want you to do it here, which is not the only way to do it, by the way, is, well, let's look at our number line. There's 0, 1, 2, 3, and 1. What we want to do is look at what happens as the graph comes in from the left to 1. So let's plug in 0. And we're going to plug 0 into the first derivative, because what we want to see is what the slope looks like as it gets as it comes into these points 1 and 3, our critical values. So let's pick 0, because remember, all we care about is 1 and 3. But there's 3 intervals there. There's an interval between these two numbers. There's an interval after 3, and there's an interval to the left of 1. So I can plug in anything to the left of 1. That would make it easy. Let's plug in 0. If I plug in 0, I can look here, and I can see when x is 0, f prime is 9. All we really care about is that it's positive. Now, between 1 and 3, we have to pick, we don't have to, but it's easiest to pick 2. So I'm going to come over here, and I'm going to show you a really nice, easy way. 3 is positive. We don't have to worry about it. If x is 2, so let's say x equals 2, then x minus 3 is 2 minus 3. And I'm looking right here. Times 2 minus 1. Well, this is a negative, and this is a positive, which gives me a negative value at 2. And also, it'll be negative everywhere between those two values, those two critical points. Then we have one more interval. Let's pick 4, because that's in the right side. So we're going to pick x equals 4. When I plug 4 into this function, I get a positive times, this is 4 minus 3, so this is positive, and this is 4 minus 1, so this is positive. A positive times a positive is a positive. Now we have something to work with. What are we going to say? We're going to say, well, this before 1, our graph is increasing. After 1, it's decreasing. At 3, it starts to increase again. And it continues to increase forever, and it continues to decrease forever. So my graph is going to look something like this, which means that x equals 1 is a local maximum. And at 3, we have a local minimum. And we don't have neither. We have one of each. So if I were to graph something, that this is the graph of x cubed minus 6x squared plus 9x plus 2. And we can see that at 1, we have a local maximum. And at 3, we have a local minimum. So just like we said, we did it perfectly. And that's really all you have to do. So another way that we can look for extreme values is by looking at the concavity. If I have a minimum value, my graph is going to open up. Since it's going to open up, just like these two graphs, we're going to have a minimum value. Think of a parabola that opens up. It has a minimum value. For those critical points where f prime of c equals 0, find f double prime of 0. Basically, we want to take the second derivative. If the second derivative is negative, so A says if f, the second derivative at some value is negative, then it's concave down. And it has a local maximum. If it's concave down, it's going to have a local maximum. B says f double prime at some value c is positive. Well, if you have a second derivative that's positive, it's concave up. So you can see that it has a minimum. And if it equals 0, it may be maximum, it may be minimum, it may be neither. We don't know much about it when it's equal to 0. We have to do a little more testing. The local extremes of a function occur at critical points. These are points in the function that we can find by thinking about the shape and using the derivative to help us. So, for example, here we have the shape. We have a local minimum here. We have a local max here. And that's about it. I'll say local max, local min, but my maximum value is right up here. And my minimum value is right down here. But you're never going to find them with critical points, because a critical point would mean that we would know that after we're here, it's going to go down. But we don't know. It could continue up forever. That's why we call it a global maximum and a global minimum. We don't know what happens before or after them. Well, we know what happens after the maximum. We know what happens before the minimum, but we don't know what happens after that. So it's the smallest point on the graph, and it's the biggest point on the graph. And when I say smallest and biggest, I'm talking about y values. These endpoint extremes are not related to the shape of the function. They have to do with the interval, the window through which we're viewing the function. Like if we were to just say, cut the graph at this point, well, now that no longer exists. So it's just, that's a global maximum at an endpoint just because of where we set our interval. That's the only reason. We don't know what's happening before or after those. So another example, f of x is equal to 2x to the third minus 15x squared plus 24x minus 7. Oh, they're being nice to us. They're telling us where our critical values are. And it says use the second derivative test for extremes to determine whether f of 1 and f of 4 are maximum or minimum values, or they could be neither. Well, first thing we have to do, they told us, we have to find the second derivative. To find the second derivative, we have to find the first derivative first. So we have 2 times 3 is 6x squared minus 15 times 2, which is 30x plus 24. That's f prime of x. F double prime, or the second derivative, is equal to 6 times 2 is 12, x minus 30. And now what we want to do is plug in these two values. First, we want to plug in when x equals 1, because that's our first critical value. When x equals 1, let's say f double prime of 1 is equal to 12 times 1 minus 30. I don't really care what 12 times 1 minus 30 is, but what I do care is that it's less than 0, so it's negative. Since it's negative, it opens down. Because it opens down, we have concave down. Okay, if it's concave down, let's draw a picture. Well, that's a maximum value. That means x equals 1 is a maximum. If I have x equals 4, that's the second critical number they gave me. So let's find f double prime of 4, which equals 12 times 4 minus 30. This is 48 minus 30, which is definitely greater than 0. So we have positive, concave, up. If something is concave up, it looks like that, and we have a minimum value. So this is our local min. So here it says if you need a product rule, quotient rule, or chain rule to find the first derivative, finding the second derivative can be really a lot of work. So also, even if the second derivative is easy, the second derivative test doesn't always give an answer. The first derivative test will always give you an answer. So just leave it at finding the first derivative and use the previous method, where you look at here where you look at the first derivative on a number line, and you can see the slope is positive then negative, and here the slope is negative then positive. So don't stress out about taking the second derivative if the first derivative was hard to do. Now, global maximum and mins. In applications, we often want to find the global extreme. Knowing that a critical point is a local extreme is not enough. For example, if we want to find the greatest profit, we want to make the absolute greatest profit of all. How do we find the global max or global minimum? Well, we find them by finding our critical points, as always, but we also have to check our endpoints. So the local extremes of a function occur at critical points. That's what we know. That's only local, or sometimes called relative. These are points in the function that we can find by thinking about the shape and using the derivative to help us. But if we're looking at a function on a closed interval, what that means is we have some specific window that we're looking at between this point and this point. Then we have endpoints, and those endpoints could be the global maximum and global minimum. So we have to go find the end and plug in that value as well to see what, if that gives us a bigger number than we get from all the other positions. Okay, so here we are at example 6, and it says find the global max and min of this function between these two endpoints. So what do? Well, first, we take the first derivative and we find our critical values. We get 3x squared minus 6x minus 9. We remember we have to set this equal to 0. And what do we find? 3. First, we're factoring out our 3. Seems like this is the same function over and over, but maybe not. No, that's not. But I can factor that as x minus 3 times x plus 1 equals 0. We have nothing that's undefined, but we do have critical values. So here our critical values are x equals 3 and x equals negative 1, because we set each one of these equal to 0 to find our critical points. We could do it two ways, okay? We can either do it finding the second derivative. So let's do it that way. So the second derivative is equal to, well, we're going to go here and look at this as the first derivative. So we have 6x minus 6. If we plug in x equals 3, we would get the second derivative equals 18 minus 6 which is positive. If it's positive, it's concave up, and it's a minimum. It's a local minimum. At x equals -1, we have f double prime of x equals 6 times -1 minus 6, which equals -6 minus 6, which is definitely negative. Do we really care about the value? No. Negative means it's concave down, and that means it has a local maximum. Now, what we have to do is find our local minimum, x and y value, local maximum, x and y value, and our endpoint, x and y values. So what I mean by that is go back to our original function, and it's equal to 3 to the third power minus 3 times 3 squared minus 9 times 3 plus 5. So this is equal to 27 minus 27 minus 27 plus 5. So these cancel to 0, and we get -22. Okay, so we have now 1 point. We have a local minimum at when x equals 3, y equals -22. Now let's plug in f of -1. So f of -1 is equal to -1 to the third power minus 3 times -1 squared minus 9 times -1 plus 5, which is equal to, so this is -1 minus 3 times 1, so minus 3, minus 9 times -1 is plus 9 plus 5, which is equal to -1 minus 4 plus 9 is 5 plus 5 is 10. So we have a local maximum at -1, 10. But I'm not done because I'm looking for the global. We found our local max, local min. If we're looking for our global max and global min, we have to plug the endpoints of the original function. So I have to find f of -2 because that's our lower bound. And that is equal to -2 to the third power minus 3 times -2 squared minus 9 times -2 plus 5. We have -2 to the third power is -8 minus 3 times +4 minus 12 minus 9 times -2 plus 18 plus 5. And this number is -8 minus 12 is -20, plus 18 is -2, plus 5 is 3. So we have another point, f of -2 equals 3. So when x equals -2, y equals 3. Well, that's not, the 3 is not bigger than our maximum, nor is it smaller than our minimum. So that endpoint, there's nothing to worry about. Neither. The last one we have to plug in is 6, our other endpoint. So we have f of 6 is equal to 6 to the third power. Oh, this has possibilities. Times 6 squared minus 9 times 6 plus 5. So 6 to the third power is 216. Then we have 3 times 36, which is 108. And it would be negative 108. We have minus 54 plus 5. This is equal to, so 216 minus 108 is 108. 108 minus 54 plus 5. 108 minus 54 is 54. Plus 5 is 59. Well, that does look like we have a new maximum. So we have a point 6, 59. We can see that that is our global maximum. It's bigger than any local maximum. We only have one other. So that's our global max. But since this is our only min, this is also our global min. So this point is local and global minimum. This point is local maximum, and this point is global maximum. And that really takes care of everything. If there's only one critical point, if the function has only one critical point and it's a local max or min, then it must be the global max or min as well. Okay, if there's only one critical point, whatever that critical point is, it's either going to be the local minimum or the local maximum, and it's definitely also going to be the global minimum and global maximum. When in doubt, graph it and look. If you're trying to find a global max or min on an open interval or the whole real line, and there's more than one critical value, then you need to look at the graph to decide whether there is a global max or min. Be sure that all your critical points show in your graph and that you go a little beyond. That will tell you what you want to know. So we have a new function. We're going to look at example 7. So we say, here it's telling us we previously found that 1, 6 is a local maximum and 3, 2 is a local minimum. This is not a closed interval, and there are 2 critical points, so we must turn to the graph of the function to find global max and mins. So what do we know? We know we have a local max at 1, 6. We know we have a local min at 3, 2. Okay. We're not on a closed interval. We have these 2 critical points. So let's find our y-intercept. Let me make these red. So our y-intercept happens when x equals 0. When x equals 0, we can see that it's going to go through 2. But 3, 2 is a local minimum. So that means it's going to come up to our maximum, go down to our minimum, and we know if it's local, that means it's going to go up again. And on the left side, we have no more local mins or maxes, so it can't turn up. That would give me another local minimum. There's only 2 critical points, which means this graph is going to come down like this. If we want to find the global maximum or minimum, we found the locals. Well, we can see that it's not this is not a global maximum because this function is going to continue to rise. And this is not a global minimum because this function is going to begin to fall. So if I say that, but we don't have a global maximum or global minimum. So to find global extremes, the only place where a function can have a global extreme are critical points or endpoints. If the function has only one critical point, we said this a little bit ago, it's a local extreme, then it is also a global extreme. If there are endpoints, find the global extremes by comparing y values at all the critical points and at the endpoints. That's what we just did. When in doubt, graph the function to be sure, which is again what we just did. Thank you for listening.